As many can attest, when you join the Censored Earth community, you are given a new set of eyes. Now, I've studied Earth science before, but now that I've been given a new set of eyes, I'm going to go back and take another look and tell you what I see.
This is Modern Earth Science Destroyed, Chapter 2.3, Artificial Satellites.
Before we begin, I must say, I've heard some comments concerning our title and the emphasis that it puts on the term destroyed. Some people have asked, why are you trying so hard to destroy what other people have built? Isn't it kind of rude to knock down someone else's block tower? Well, let's describe what a pitfall is. A pitfall is a trap where someone digs a hole and then covers it up to make it look like the ground around it. Then, when someone walks onto it, thinking it's solid ground, they fall into it. These are also called tiger traps, and sometimes people would put spikes on the bottom of them. From what I understand, these were unfortunately abundant throughout the Vietnam War. Now tell me, is it rude to expose and point out academic tiger traps like these and destroy them? No.
That is a really good way of looking at it. When a teacher or a textbook teaches a concept with little to no observations to back it up, they create academic tiger traps. I see no shame in destroying those.
Exactly. Now let's see what pitfalls we can find this time.
Chapter 2.3, Artificial Satellites.
If you drop a ball, it will fall straight down because the force of gravity pulls objects toward the center of the Earth. If you throw a ball horizontally, it will follow a curving path. The force of gravity still pulls the ball toward the Earth, but the ball also moves horizontally as it falls. The greater the speed at which the ball is thrown, the farther it will travel before gravity pulls it to the Earth's surface. For example, a ball thrown at about 8 kilometers a second and not slowed down by air resistance would follow the curve of the Earth. As shown in Figure 2-11, the ball would fall toward the Earth, but never reach the Earth's curved surface. Instead, the ball would become an artificial Earth satellite. A satellite is any object in orbit around another body with a larger mass. Do you see any pitfalls mentioned there?
Well, they did mention gravity 3 different times there. As I remember back in Chapter 2.1, we pointed out how gravity is a fictitious force. Here is a link to that in case anyone missed it.
Yeah, treating fictitious forces as if they were real? That is just like treating this ground as if it were real. That is a pitfall for sure. Alright, now, looking through here, I get the concept that they are teaching about how the harder you throw a ball, the longer it will stay in the air. Then all of a sudden we get down here and they say how if you throw a ball hard enough, it will never reach the Earth's curved surface. Should I agree with them on that one or not?
Because you're a censored earther?
Exactly. We teach an entire course with over 100 lessons debating that topic right there, as to whether the Earth is curved or not. Here's a link to that if anyone's interested. But let's not get into that here. Anyway, I think it's interesting how they claim the ball would never reach the Earth's surface. Here they mentioned 8 kilometers per second, which I can't help but think is a rounded number for the speed of the International Space Station that is said to orbit the Earth at 7.66 kilometers per second. Not even Space.com claims the ISS will never reach the Earth's surface again. Its direct quote is here. It needs a regular boost or fuel injection from visiting spacecraft. If those boosts stop, or something else goes wrong, sooner or later the lab will fall. So who's wrong here? Is the textbook wrong? Is Space.com wrong? Or are they just unable to reach that perfect speed of 8 kilometers per second? Not that I believe the ISS is actually up there or anything. I just thought that was interesting.
That is interesting. Although the book here mentions something about the ball not getting slowed down by air resistance. So perhaps Space.com's reasoning is that the space station experiences just enough air resistance to eventually send it crashing down to the Earth.
I have to give a special thanks to a member of our debate board by the name of Jeffrey Pinion, also known here on YouTube as Night Sky Jeff. He was able to contribute an interesting article from History.com about the Skylab, which is said to have crashed back in 1979. Apparently it was a predecessor to the ISS, and in order to keep it up there, they would have had to give it continual boosts. But eventually people lost interest in keeping it going, so they just let it crash. In all this, there was no perfect speed to make it stay up there forever.
Looking at the article further, the authors put a lot of emphasis here on the concern of the impact hurting someone. So they fired up the Skylab rockets and launched it at the Earth even faster. It makes you wonder why they didn't use the rockets to turn the Skylab away from the Earth and launch it out into space where it wouldn't hurt anyone.
It seems they just couldn't do that. It may very well have been a publicity stunt. According to the article, it was in the midst of declining confidence in the US government. It could have been their way of saying, hey, if you don't shape up, you're going to lose your space programs. But in the end, people held parties and celebrated as they watched it burn and made fun of the government by selling cans of Skylab repellent. Thank you for sharing, Jeff. That was a good article. There's a link to that in this video's description if anyone would like to read that for themselves. Alright, I'm going to take another look at this real quick. If you drop a ball, it will fall. That is an observation of downward force. Gravity pulls objects toward the center of the Earth. That is a tiger trap because we don't see any observation supporting that claim. If you throw a ball horizontally, it will follow a curving path. Yes, an accelerating vertical force plus a horizontal force equals a curving path. That is an observation. The force of gravity still pulls the ball toward the Earth. That's still a tiger trap. The ball moves horizontally as it falls. That's an observation. The greater the speed at which the ball is thrown, the farther it will travel before it hits the Earth's surface. That's another observation. If you were to throw a ball at 8 kilometers a second without any air resistance, the ball would never hit the Earth. That isn't an observation. It is a complex concept. And what makes it that is the fact that it depends on another concept in order to be true. That concept is the claim that the greater the speed at which an object is thrown, the slower it will fall.
I can see how that might be the case with air resistance, but without air resistance, I don't see any observations supporting that claim.
And that's what makes it a tiger trap. A horizontal force can't negate or cancel out a vertical force. That is an observation.
Now, let's talk about the way they define satellites here. Here they say a satellite is any object in orbit around another body with a larger mass. What about balloon satellites? Do they orbit the Earth?
Let's look up the word orbit in the dictionary. Dictionary.com describes the word orbit as a curved path, usually elliptical, described by a planet, satellite, spaceship, etc., around a celestial body as the sun. So it seems a circular or elliptical path isn't required. So according to the definition, if I were to throw a ball on a curved path, that could be considered throwing a ball into orbit. That means throwing a ball in such a way at 8 kilometers a second so that it travels all the way around the world? That's irrelevant. Because, by definition, every ball you throw that has a curved trajectory can be considered an artificial satellite.
Oh, okay. So as long as this balloon goes up and travels in a curved path, then that can be considered orbiting the Earth.
Yes, thereby every rocket that gets launched They can all be considered going into orbit. Uh-oh, it looks like Jeff has something to say about that. He wants to emphasize the word around in our definition of orbit. So let's take a look at the definition of the word around. In definition 5, it reads in circumference, as in, the tree was 40 inches around. By this definition, in order to be considered a satellite, an object would have to travel the entire circumference of the Earth. But here in definition 4, it reads in a region or area neighboring a place, as in all the country around. So by this definition, in order to be considered a satellite, an object just has to travel to a nearby place.
It looks like definitions 15 and 16 follow that same line of thought. Okay, so thereby going into orbit doesn't require an object to go all the way around the Earth.
Yep, let's continue reading.
Satellites and orbits.
Today, hundreds of artificial satellites orbit the Earth. Meteorological satellites gather and transmit weather information. Communication satellites relay radio, telephone, and television signals to and from various locations on Earth. Navigation satellites send out radio signals that help pilots of ships and aircraft determine their locations. Scientific satellites and orbiting telescopes are outfitted with special instruments that allow scientists to study the distant reaches of space.
You know, it's a pity the book doesn't show pictures to reference any of these satellites.
I totally agree. Satellites are put into orbit by powerful computer-guided rockets. A rocket carries a satellite to an appropriate altitude above the Earth. The rocket then aims the satellite at the angle necessary for the desired orbit. Once the satellite is in place, the rocket automatically detaches from the satellite. A smaller rocket on the satellite may provide the extra speed necessary to send the satellite orbiting around the Earth. The Earth's gravity holds the satellite in orbit. Yeah, you know, if I were to duct tape my cell phone to a rocket, it would make it heavier, and that would affect its trajectory, which would mean that I could say it's computer guided, and I could even say it's got GPS. It's now a satellite phone! The altitude of a satellite determines the speed necessary to keep it in orbit. As the distance from the Earth increases, the force of the Earth's gravity decreases.
There they go again, acting like a horizontal force can negate a vertical force.
Yep. Air resistance is also reduced in the Earth's thin upper atmosphere. Therefore, the higher the orbit of a satellite, the lower will be the speed needed for it to stay in orbit. At an altitude of 36,100 kilometers, a satellite completes one revolution in 24 hours. At this altitude, a satellite in orbit directly above the Earth's equator and moving in the direction of the Earth's rotation is in geosynchronous orbit. A satellite in geosynchronous orbit always remains at the same point above the equator and appears to be stationary in the sky. Satellites used for communications are usually put into geosynchronous orbits. High above the Earth, these satellites can act as antennas, relaying electronic signals over great distances. Some weather satellites use this high stationary orbit to continuously track hurricanes and other storms.
I wonder why they claim a geosynchronous satellite has to be above the equator. It isn't that hard to inflate a balloon and make it look stationary in the sky.
Yeah, you don't have to be in Ecuador to do that.
For that matter, if every stationary balloon in Ecuador can be considered a geostationary satellite, that tells me there could be quite a bit more than a few hundred satellites orbiting the Earth.
That's a good point. On that note, Did you know that according to the news, there is a worldwide helium shortage going on? Guess who the world's #1 consumer of helium is?
I'm gonna guess NASA?
It's NASA.
Isn't that suspicious?
A satellite can also be placed in a polar orbit. A polar orbit carries the satellite over the Earth's north and south poles. As the Earth rotates beneath it, a satellite in polar orbit passes over a different portion of the Earth's surface during each revolution. After a certain number of revolutions, the satellite will have surveyed the entire surface of the Earth. A polar orbit is useful for mapping the Earth's surface and for tracking weather. Why might a polar orbit be better than a geosynchronous orbit for some weather satellites?
That reminds me of what we observed in Google Maps. Here in the Google Maps satellite view, it's easy to see all these strips or these lines going from north to south. And when you zoom in right between the columns, you can get an idea of just how far away the satellite really was when it took the picture.
Yeah, it looks like that picture could have been taken from a plane.
That definitely doesn't look like it was taken from this high up. If it was, I think each of the strips would be much wider and you would probably see some clouds below.
Most satellites follow slightly elliptical orbits around the Earth. The point closest to the Earth in the orbit is called perigee. The point farthest from the Earth in the orbit is called apogee. The satellite travels fastest at perigee and slowest at apogee.
That sounds like what we were talking about last time with the aphelion and perihelion.
Yeah, there's been some discussion about that on our debate board. But so far it has just been people claiming that it is possible, not really explaining how it is possible. For the sun to have a stronger attractive force on one side of it than the other, which creates the elliptical orbit. And now they appear to be claiming it is the same thing with the Earth. If that is the case, then I would expect people on one side of the Earth to be heavier than the people on the other side of the Earth. Perhaps that is just one more excuse for America's obesity epidemic. If anyone would like to come and discuss this on our debate board with us, please feel free. To stay in orbit, a satellite must maintain a speed adequate for its altitude. If the orbit comes too close to the Earth at perigee, friction with the Earth's upper atmosphere will slow the satellite down. This decrease in speed means that each successive orbit will bring the satellite closer to the Earth at perigee. Eventually, the increasing friction of the Earth's atmosphere will generate too much heat and the satellite will burn up.
Now, here is something I'm wondering about. As we know, if I were to jump off of the top of a ladder, it'll hurt more than if I were to jump off the bottom of it. That is because the more time I spend falling, the faster I fall. Now, if a satellite is perpetually following around the Earth, why isn't it continually going faster and faster, just like me jumping off of the top of a ladder?
That's a good question. Does anyone have an answer to that? That one basic observation of falling seems to utterly destroy the traditional concept of how satellites are supposed to work.
Exploring the Earth by satellite.
Satellites have given scientists new ways of studying the Earth. Some of the most fascinating information has come from a series of American scientific satellites called Landsat. Each Landsat orbits the Earth in a polar orbit and collects information using electronic sensors. The resulting images are used to identify features on the Earth's surface, such as cities, vegetation regions, and even rock types.
I definitely have to wonder what those satellites look like.
I'm glad you brought that up. I think it's interesting how NASA considers this unmanned drone to be a satellite. I've got a link about this in this video's description if anyone wants to check that out. The Global Positioning System, or GPS, is a network of satellites used for accurate navigation of ships and aircraft. Even with a small handheld receiver, The system can locate virtually any point on the Earth's surface with an accuracy within several meters. Most satellites are designed simply to receive information and send electronic information back to Earth. The Space Shuttle, however, is an exception. This temporary satellite is designed to carry cargo, orbit the Earth, and then return to the Earth's surface. While in orbit, the shuttle can release or pick up other satellites.
Well, that finishes all of Chapter 2. Chapter 3 is about models of the Earth. There we will talk about maps.
I look forward to that.
Thank you for watching.